So let's wait for Vanit. Sorry for that. For some reason, it jumped the host from Vanit Agrawal to, to Sarah. But yeah, Vanit, I will make you the host where you can do everything. Okay? You are the host. Thanks. Yeah, you are the host now.
All right, can you see the whiteboard?
Yes, we can see.
Okay, thanks a lot.
Yeah,
Hello, everyone. So today we'll start with the second lecture. And in this lecture, we will talk about finite Markov decision processes. Markov decision processes are also called, in short, MDPs. So the key things that we will use in the Markov decision process is what we introduced last time. We have an agent and an environment, which we discussed in detail in the last lecture. Agent observes a state, takes an action, and the environment updates the state and provides a reward. So just to give back the figure that we drew last time. So agent has an input state, takes a decision AT, which goes into the environment, which updates the state and then provides a reward. So the state of state set is denoted as S. Actions belongs to, since I can't write calligraphic or non-calligraphic that well, so state set is 1 to S. Actions are 1 to A. And the reward belongs to a real number. So by finite Markov decision process, I mean finite states and finite actions. So S and A are finite. The environment provides updated state and reward. We define the transition probability of the environment, which is called the model. In the last lecture, we defined 4 things. The 4th thing among the key notions of reinforcement learning was the environment model, which is probability S prime comma R given S comma A. This is probability that ST equals S prime, RT equals R given ST minus 1 equals S and AT minus 1 equals A. So given the previous state was S and the agent made a decision A, what is the probability that the environment will have the next state as S prime and the reward as R? Is this definition clear? So
yes,
this transition,
thank you. It's clear.
Thanks. So this transition probability is what we call model of the environment. This probability may or may not be known. For the case of Markov decision process, we assume, and for today's lecture, we assume that this probability is known. But in many general situations, this probability of the state and reward update may not be a priori known, and we may need to learn this probability using some data or some actions in the meantime. So since this is probability, sum over S prime and sum over R P S prime R given S comma A will be what? When I write sum over S prime, it means sum over S prime equal belongs to 1 to S, the entire range, if I don't define the limits. So what should this probability be? Since it is probability, sum of probabilities is 1. Yes, correct.
All the probabilities, right? Sum of all probabilities should be 1.
Yes, that is the basic thing, that this is probability, sum of all probabilities is 1. Now, if we have to find P S prime given S A, this is called the state transition probability. What I'm doing is I removed R from the top numerator of probability. So this is probability ST equals S prime given ST minus 1 equals S and AT minus 1 equals A. How can I find this probability from P S prime R given SA? So I have P S prime R given SA, and I need to find P S prime given SA. What is the easy method? Exactly, sum over all possible values of, no, I don't need sum over all possible values of S prime, that would remove S prime. But this is close, I need sum over all values of R. Okay.
Kind of conditional probability.
Yes, but given S comma A is the same, so if I have to find S prime, I sum over R.
Doesn't it have?
So the condition remains the same. We are basically summing over R, that would give me P S prime given SA. So the next thing is expected rewards. It is denoted as RSA, which is defined as expected value of reward at time t given previous state is S and previous action is A. So in order to find this, we need intuitively summation R times the probability of reward S t minus 1 equals S and A t minus 1 equals A. And this probability, as we know, could be found as summation over S prime P S prime comma R given S comma A. So this summation is dual of this, where here we summed over R and here we are summing over S prime to find the probability of reward. Okay, so RSA is then given by this expression. So knowing the probabilities, we also know the expected rewards. Any questions so far?
Yeah, Banit, I would say,
Yes.
Is there a calculation example that would help later on, even if it's not today? Okay, to just to show, like, as an example, how we would calculate these. I'm sure, in the long calculation and complicated calculation, we may need some programming, maybe coding, dynamics code to do this, isn't it?
I don't have something to compute these probabilities, but I will give example for just the transition probability.
That's good.
But
Even
yes,
if you send it, so we could read it and ask you later. You
Sure.
don't need to explain it now. I mean, it's not ready now. It takes time. Okay?
Sure. So this Markov decision process is applicable in many scenarios, as we discussed even in the last time. Wherever you have to make any decision, any goal-oriented learning, you will need that. You get a reward at each time, which is RT. You get the state update based on the past, which is ST plus 1. One of the example that we'll do for this type of formulation is recycling robot. So this is the model is there is a mobile robot. The job of the robot is to collect empty soda cans. In office. So the robot has sensors. So there are sensors for detecting cans. There's an arm. There's a gripper. So the gripper can pick the soda can and put them in the bin. The robot runs on rechargeable battery. So the basic component of the robot's control system is that you can have sensory information, you can control and navigate the arm and gripper. So the robot has to make decisions based on what it sees, as well as how much is the current charge of the battery. The decisions action can take are should it actively search for can? Second option is it can stay stationary for some time and let someone bring a can. And the third option is head back to base to recharge. Is the model clear? So these are the decisions which we will model in the state of actions. The second thing that we will model is what is the state. We assume that these decisions are only made based on the state of the battery. So what happens if the battery level is high? Then what does the robot has to do? If the battery is low, what does the robot has to do? So those are the state, and next we'll also define the rewards. But just to make it simpler, we make the state, the battery level, only in two possible levels, low or high, just for our ease. Okay, and the actions, we define them as three possible options: search, the second option is wait, or the third option is recharge. So the possible set of actions when in state high are you can search or wait. If your battery is already high, there's no need to recharge. But if you're in low, your set of actions is you can search, wait, or recharge. Is the setup clear? Or any questions so far?
Yeah, the last line is not appearing, Benit. I think A of high is one of the search or wait, like, you know, then the line underneath this is we don't see it for some reason.
Okay, so what I wrote was A of low is search, wait, and recharge.
Oh, okay, okay. So just A of low and A of high. Very good.
Yes. So if you're in low, you can search, you can wait, or you can recharge.
Also, this is from the third chapter, right, of the book?
Yes, this is. There was a question, let me repeat. If it is low, why searching? It is low but not depleted. So there is a third possibility where you could have depleted the battery. So if it is depleting, then of course it does not search. But in low, it can still search till it is depleted. So that is still a possibility that we are including. So we also have to define the state transitions. So P, S prime are given S comma A. In order to understand that, what we will assume is that in the searching phase, if your action was to search and the battery was high, we will have remaining battery after the search as high with probability alpha and low with probability 1 minus alpha. Okay. If the search is undertaken at a low battery state, then you have a low with probability beta and deplete with probability 1 minus beta. So if you go to the deplete state, the battery has to be rescued since we're not including this in the state. So what happens is the battery will be rescued or the robot will be rescued. And there will be a negative reward because somebody has to take the robot to the recharging. Let us call this negative reward, just to put some number, as -3. Okay. Or let's say our search is the average reward, which is the average number of cans which are picked up in the search phase. And our weight is the average reward for the weight. Is the definition of our search and our weight clear? So these are average number of cans, which is the same as average rewards that you get if you execute the search action or the wait action. We assume that searching is better than waiting, so our search is better than our wait. Okay, so that is the basic setup. So now let us use this to come up with a state and reward update table. So we have the current state, the current action, the next state, the probability that you go to state S prime given S comma A, and the reward S A S prime. Before I go here, let me define one more thing. Okay, so we defined RSA as expected value of reward given as t minus 1 equals S and A t minus 1 equals A. There's another definition which is called expected reward for state action next state pair, or if there are 3 arguments RSA prime. This conditions on one more thing: expected value of reward given st minus 1 is S, at minus 1 is A, and st equals S. Of course, you can get the previous one by multiplying over P st equal to S given the other things, which is the transition probability, and summing it over. using the law of conditional probability. So without going over the complete mathematical proof, this can be easily written as summation over R P S prime R given as A divided by P S prime given as A, where the denominator was also defined before as the state transitions. Okay, with that definition, we'll start filling this table. So if the current state is high and we performed a search, what could the next state be? In high, if we performed a search operation, where all could we go? If we are in state high and we performed a search, where all can we go? Yeah, high or low, high with probability alpha. So that's exactly what I'm writing here. You could go to high or low, high with probability alpha, low with probability 1 minus alpha. Okay. If you go alpha high, or if you're in high and search and you go to high, what is the reward you get? If you're searching, what is the reward you get? R search. Okay, what happens if you go to low? Does it change? No, because you're still searching and you will find R search number of soda cans. Clear so far?
Yes.
Great. Okay, now let us assume you were in low to start with and you perform the search operation. Where all can you go?
Either low or deplete.
Yes, but deplete was not a state. If you go deplete, you go to high after somebody rescues you. So you still go to high and low.
Yes, high and low.
So what is the probability that you are in low?
One minus beta.
Did we define as 1 minus beta or beta? If you're low, you remain low with probability beta. Okay, so if you're low, you remain low with probability beta and high with probability 1 minus beta. Okay, so what is the reward you get in this state? If you search and you deplete, you do not get anything, but you have to be rescued. So if you have to be rescued, what is the reward? We assumed that to be -3 in the previous slide. And if you searched and you remained low, what is the reward you get?
R search.
R search, yes. Okay, so there are 3 possible SA S prime, means each in 2 of the states, so there would be 8 combinations here. Sorry, 2 times 3 times 2. Action is action has 3 possibilities. Okay. So now let us assume that you were in high and you waited for somebody to come and give you the soda cans. You could still go to high or low. Okay, if you're waiting, you're not using any of the battery.
So it should be the whole thing, right? 1. The whole thing.
So this would be whole thing 1. Yes, this is 0. Okay, if you're waiting, what is the reward you get? R wait. And same here, R wait. Okay. So you could be in low to start with, and you could wait. Okay, if you wait, you could still go to high or low. Let us see the probabilities of them. If you're in low, what is the probability of going to high after waiting?
I think, yeah, opposite. It's 0, 1.
0, 1.
Yes. And the rewards, you are still waiting. So R wait and R wait. Okay. So you do not recharge when you are in high. So you only recharge when you are in low. So if you're in low, you could go to the recharging station and go to high, or you can go to low, recharge, and then low. What are the probabilities of last two?
Could be 1, the first one.
And 0. And you are going to recharging station, you are not finding any soda cans, so your reward is 0. Okay, so you already got all these transition probabilities using which you can compute whatever is needed for your behavior. So this is how, in an example, the transition probability works. Does that make sense?
I have a question.
Sure.
Then this, when you say the model, one of the component is the model, right? To make
Yes.
a model, is it possible that this table will direct us to draw a model, like, you know, it's kind of a graph theory, kind of, I don't know. I'm not sure if what I'm saying makes sense or not.
Can you please explain what do you mean by this is graph theory?
Well, it's just like, you know, just like connecting, you know, like, you know, it's you're making trees, kind of high.
Yes.
Branches from high or high search, okay, 1 branch, and then 2 branches after search, high and low, and then this will take values. So it's just like, you know, it's not really a graph theory, but it's kind of like, you know, part of it. It's like, you know, we are having vertices and graph, okay, and having values of functions, which is the probabilities, the rewards.
Yeah. So
yeah.
Essentially, it would become a series of decision over a large enough horizon where you have to keep on taking actions which influences the next states. So essentially, you are going down a tree. So in that sense, the connotation is right. So the model essentially is that you know all these things to start with before making decisions, and the decisions is still to choose A's at each time. So here I'm giving you a graph or a table, but I'm not telling you what is the policy or what is the action you should be taking at different times. So this is an input to our decision maker. Does that make sense?
Yeah, so it's which part of our component in reinforcement learning now, this one, this thing.
Yes, so this is an input for Markov decision process. So there was a question on the chat window of the third line that we are not going depleted, but deplete was not taken as a state. So if you go from low to high, that essentially means that you depleted the battery. And that is why you had to be rescued. Since you had to be rescued, the reward was -3. Is that clear?
Well, it's not really clear, you know, but can you go to the previous one? You get it from what you have wrote in the previous one, right? So we have low, search, high, okay? And 1 minus beta. And then the
Yeah,
reward
so
was -3. How you get it? Yeah.
Yeah, if you go to deplete, then you have to be rescued and you get a negative reward. But after rescuing, you go to a state high. Right? Because once you are rescued to the charging station, you will go high. So you'll go from low to high, but with the cost of -3.
Oh, which is receiving a negative reward in this case. Yeah.
Yes. Okay.
Thank you.
Any questions with this? Okay. The next thing is what we discussed before. What is the concept of reward? Reward is what you get at each time. But in general, we don't care about rewards. We care about the sum of rewards over the future time. Y -3 not any other value. This was just an example, and you could choose any numbers you want. You could choose it -100, that is fine. So that's something that we chose in the example. Okay. So overall, we do not care about reward at time t, but we care about the future rewards, which is what we call expected return. Which is GT given as RT plus 1 plus all the way till RT. So now this definition puts us into a question, what is capital T? So expected return is defined from the next time till the infinite, till the end of the time. Now we need to define end of the time. If we are summing a reward till infinite, there is a issue in the sense that a constant summed infinite times is infinite. So we cannot be comparing between two different infinities. So there are two approaches that are typically done. And the two approaches are episodic and non-episodic. What episodic assumes is that you have a finite time horizon. So T is finite. So let me give you example. You are playing a game. The game has an end. Two players are playing in a finite number of moves. The number of moves could be stochastic, so T could still be a random variable, but not infinite. So you're playing the game will end at certain point, and then it would restart. So those type of situations is what we call episodic. So each game is run in an episode. So you'll have a terminal state, you'll have a time where you win or lose, and then you restart the setup. So that is called episodic, where you, at every time in the episode, so you have a time which you are dividing into episodes. each of length t. T could be a random variable, and so on. At the end of every episode, your state restarts to the original state. Okay, you are starting to play a chess. After the end of the game, which is an episode, you basically put the pieces back to the original form. So that is called an episodic environment. In this situation, the above definition kind of makes sense. You can have the sum of rewards from every time t, the rewards after that time till the end of the episode, and the expected value of that is what we will use as the objective. Is that clear? Is the episodic setup clear?
Yes, yes.
Okay. Non-episodic is that the time is infinite. So if the time is infinite, then this definition does not work. So this definition only works for episodic case. And the reason it does not work is exactly the same thing, that the rewards, if they are infinitely often a positive quantity, then your rewards will, then GT will go to infinite, and you'll not get any meaningful number out of it. So in order to deal with that, we use discounted reward. Which is GT is RT plus 1 plus gamma RT plus 2 plus and so on. This is infinite, so it keeps on going till large enough time. Just in short form, this is sum over k from 0 to infinite, gamma k RT plus k plus 1. So gamma is chosen to be something less than 1. Even if all the rewards for the future are 1, the sum of gamma k converges. So the definition makes sense. We choose 0 less than equal to gamma less than equal to 1, which is the discount rate. And I've put less than equal to 1 to include both the definitions, but keep in mind that gamma will not be 1 for non-episodic. Otherwise, your sum of rewards can go unbounded. Any questions with this definition? So what this is doing is, this is decreasing the value of future rewards. It cares about current more than the future, and so on. If you're getting a reward after k times, it is only worth gamma to the power k minus 1. If you choose gamma equal to 0, then you care only about the current time and not about the future. And that is what we call as myopic strategy. So if we have to take an example, let us say there is a chess game, and the reward is 1 only at the time where you win the game, and 0 otherwise. Okay, so reward is 1 only when you win, and 0 otherwise. Okay, in that case, the reward is basically gamma to the t. There's only one k, where k is the time to win. So essentially what you are doing is, by optimizing this metric, you are of course trying your best to win, because that's the objective, but you are also reducing the time or the number of steps it takes to win. So if we did not have gamma, it would basically be you just have to win, whether it takes a large amount of steps or less amount of steps. The number of steps does not matter. By having a gamma, we also prioritize on getting the play finished faster. Okay, so that can give you a trade-off between whether you want to finish faster or you want to be perfect, and it does not matter when you finish it. Any questions? Okay. So later on, if you would be interested, there's a platform called OpenAI Gym that has many examples that you can play with. One of the very easy example that they call as cart pole problem. The code is written, you can definitely play with it at any time. So in the cart pole problem, what you have is there is a road, there is a cart. So these are the wheels. And on top of a cart, you have an inverted pendulum or a pole. So you have a stick type of thing hanging on top of this. The problem is that you have to balance this pole such that it is within a certain degrees. So let us say you want to keep the pole such that from the vertical, it is within plus minus theta, plus minus, let us say 15 degrees. Okay. When you say you have to win, do you mean number of moves? It is the number of moves depending on what we define as the time or epoch. And usually in game playing, we will define the time based on the step, which is playing. So in cart pole problem, is the answer clear? So it is the number of moves. Okay, so you have to maintain the pole within plus minus 15 degrees. So in this case, we define, we can have both finite horizon as well as infinite horizon. In finite horizon, we say when you go more than 15 degrees, we restart the system and put it back to the original situation. The second is you basically just assign a negative reward on each failure. So finite horizon is basically episodic. In episodic, restart after 15 degrees or fall. We assume that after 15 degrees you will fall. And non-episodic, give negative reward on falling. And keep going. Okay, of course, once you have fall, you cannot keep going. It is always, the reward is always 0 after that. So we are assuming that reward is always 0 till you have not fallen. And the reward is negative when you have fallen. So let us say reward equals -1 on falling, which is you've gone beyond 15 degrees, and 0 otherwise. Okay, in this case, the return GT using gamma is minus gamma to the k, where k is number of time steps or number of steps before failure. So you are maximizing minus gamma to the key k, which essentially means you are maximizing the time it takes before failure. Is the problem setup clear?
Yes.
Okay. Yeah, so somebody asked in the chat window, can we have a worked example? Sure, means whatever I'm doing so far is from the textbook, so you can do the example. Just that I've not even defined yet what is the policy. So this is only setting up the problem, while we have not even come up with an algorithm of, given the state transition, how do you design your action space? Does it make sense? So in order to work out, we would still need to have the algorithms. Any questions so far? Okay. So the next topic, which is the key point, is policies. So policy is what we need to design, which is what should you be doing. We denote the policy by pi. So what should the policy be doing? What should be the input and what should be the output? It observes the state and takes it into action. So this is denoted as pi of A given S. Is that clear? So this is the policy the agent will be taking. It observes a certain state and takes an action A. And by writing it pi, I'm assuming that my policy is also stochastic in general. And this is basically what I have to design. Okay, before I design the policy, I need to define, I need to explain how do I measure the goodness of the policy. And that is based on the return. So that is what I define as value. So I define value of a state as. So if I define value of a state, it is with respect to a certain policy. So value under a policy pi of a state S is the expected value under the policy that I get a return GT given that my current state is S. Is the definition clear?
Yes.
So given the initial state, if a policy has better V pi, that is my best policy. Okay, so V star as will define the the optimal one later, but this is the value of any state. We also define another function which is called the Q function. So Q function under policy pi of S comma A, intuitively the same thing, just that we condition it also over the action. GT given ST equals S and AT equals A. This is called either the Q function or the action value function. So both of these functions are dependent on the policy. Okay, and these will be the objectives that we will use to come up with the best policies. So the things that we will have to do first is to explain, given a policy. So the first question is that we'll answer next time. Given policy, how do you find V by S and Q by SA? So you already have the definition, you have all the transition probabilities. Assume a certain policy. For example, we did the mobile robot example. Take any policy that, okay, in the search space, you are in the high state, you are choosing the search and weight equally likely. So take certain policy that you want and try to evaluate these things, and we'll go more detail into how to find the notions of V and Q in the next lecture. So there are two things that are needed. First is, how do you evaluate these terms? Second is, what would be the properties of the best policy? And the third will be, how do we find a policy that reaches the optimal policy? So those are the three key questions that we still have to answer. So given policy, find this. Second is properties of optimal policy. And third is find policy that is optimal, that reaches optimal. So given that we are already at time, these are the three questions we will answer in the next lecture. Any questions?
Thank you, Dr. Vineet. The last three questions will be from the same chapter, chapter 3?
Yes.
Okay. So if anyone has a question, please ask, or you can use the chat window. Okay, thank you, Dr. Vineet, for the very informative lecture today. We hope to see you all the next lecture, which will be held on Wednesday, July 15th at the same time. Thank you.
Thanks a lot.